Ready for the final?
Yep.
Getting there. All right. So I have a review session scheduled for tomorrow at noon. It will be in ALS 4001. And I will videotape it as before. And if you can be there, great. If not, watch the videotape, etc. I will be in my office on Monday morning, so if you have questions before the exam, feel free. I'm happy to answer them for you. And I think that's all the announcement. Oh, for those of you who had regrades, I have them in my office. If you want, follow me back, and I'll give them to you. If you haven't picked up your exams before, follow me back. I'll give them to you also. And a question back in the back.
And that was ALS 4001.
ALS 4001. Yes. Okay. All right. Well, in keeping with the rest of the term, we don't have any lights on anything on the side, but rather than futz with it, I'm just going to go forward with this. I think everybody can see the middle one okay. Last time when I finished up, I was talking about the urea cycle. And I'm going to leave that as it is. I'm not going to say anything more about the urea cycle. I want to say a few things about nucleotide metabolism. And nucleotide metabolism is, I think, I won't say it's the most interesting pathway, because the pathways that really tell us a lot about our metabolic energy and so forth, I think, are more interesting. But nucleotide metabolism is of interest for one particular reason, and that particular reason is that it's the most regulated of all the pathways. It's really tightly controlled, and the reason it's tightly controlled is because if cells make too much of one nucleotide or too little of another, they are much more prone to suffering mutations. Mutation, mutation, mutation. So they have a lot of elaborate controls that keep themselves from making too much of one or too little of another. Okay? So, and in addition to that, with nucleotides, we have really two considerations. One consideration is what's called de novo synthesis. That's D-E-N-O-V-O, meaning starting from new. And de novo synthesis is literally making nucleotides from scratch. And as I will show you, nucleotides are made from very, very simple building blocks. Very, very simple building blocks. Okay? Besides de novo synthesis of nucleotides, there's also what's called salvage synthesis. And as its name would imply, salvage synthesis involves synthesizing nucleotides using pieces of existing nucleotides. So for example, imagine a cell ingests a stretch of RNA. Okay? And it has nucleases that start breaking down that RNA. Well, it could actually break those individual nucleotides down into components and oxidize them as carbon dioxide and so forth. But the cell might also be needing nucleotides. So rather than completely digest them, it may turn around and use those to make new nucleotides. That's called salvage synthesis. Just like if you were at an auto salvage yard and you needed a starter for your car, okay, it would be cheaper for you to get one out of a junked car than it would be to go buy a new starter, for example. That would be salvaging a starter. So that's what the two things that happen in nucleotide synthesis. What we see also is that purines are synthesized separately from pyrimidines. No big surprise, because they are fundamentally different from a chemical perspective. So I want to start by talking about purine biosynthesis. All right? And there's nothing on here you need to memorize. All right? So I'm just showing you this figure to give you an idea about where all the individual pieces of purine nucleotides come from. All right? So I said from very simple things, and they are. Okay? There's a carbon from carbon dioxide. This nitrogen comes from aspartic acid. This carbon comes as a single carbon from folate. Okay? This nitrogen comes from glutamine. All right? This nitrogen comes from glutamine. This central portion right here is basically glycine. And over here, last but not least, we have another single carbon that comes from another folate. All right? What we know about the synthesis of nucleotides is that the primordial things that were on the face of the earth, okay, were there that can come together and make bases. They can make those bases to make nucleotides very, very easily. Okay? We can actually see in meteorites that fall to Earth, okay, compounds that have structures very much like this, telling us that the basic chemistry that's there for making these things are out there existing. All right? And so it's one of the reasons we get very excited about the possibilities of life elsewhere, because we know that there's nothing unusual about the chemistry going on Earth compared to anywhere else. Okay? Let's see. Hold on here. It's not quite where I wanted to be. Let me give you a view of the synthesis, and then I'm going to come back and show you that last figure in a second. All right? Now, nucleotide synthesis is very elaborate. There are 10 reactions that give rise to purine nucleotides starting from scratch. We're not going to go through those reactions. It's not really a good exercise for us because, to be honest, it's nothing more than just a bunch of memorization. And I don't think that memorization is particularly useful for you. But I do want to say some things about the synthesis of purines in general. All right? One is that the synthesis starts with a ribose 5-phosphate. That's a starting point for synthesis for the nucleotides. Remember that a nucleotide has a base, it has a sugar, and it has a phosphate, at least one phosphate. All right? So we're starting with the sugar. Where does that sugar come from in our cells? Pentose phosphate pathway, okay? That pathway that keeps coming up. Pentose phosphate pathway is our source of ribose 5-phosphate. Okay? You see a series of reactions here that go down to something called IMP. And IMP turns out to be a sort of a base. It's not really a base, but it's called inosine. And you saw inosine somewhere in the class this term. Does anybody remember where they saw inosine? tRNAs, very good. tRNAs in their anticodon have inosine sometimes. Why do they have inosine there?
They don't have to.
You're there. Inosine can pair with more than one thing. So it means they don't have to make all of the possible combinations of the anticodon. In the wobble position, you will frequently find an I. Okay? Now, inosine is not a nucleotide, okay? Although it looks very much like one. Inosine we show on this scheme because it's a branch point. And this branch point I want to talk about in a little bit of detail. All right? It's a branch point between the synthesis of AMP and GMP. Okay? AMP, of course, is adenosine monophosphate. GMP is guanosine monophosphate. All right? These are the two purine nucleotides. And the way that the cell gets from IMP to AMP and the way the cell gets from IMP to GMP is really interesting. It shows us something about this regulation that I'm telling you about. All right? What happens? Well, there's a couple of reactions, and again, we don't need to worry too much about the individual reactions, but I want you to look at what's happening here. IMP goes over here to this guy, and we see that energy for this reaction comes from GTP. And over here, I see IMP goes to XMP, and XMP goes down to GMP, and the energy comes from ATP. Now, this turns out to be a very important balancing, number one. It makes sense that the energy for making AMP would come from something besides ATP, because the cell's trying to make adenosine nucleotides. Right? So GTP being a source of that energy makes perfect sense. And conversely, having ATP as the energy source for making GMP makes perfect sense too, because you're trying to make guanosine nucleotides. So we already see a balance. And one of the things that we see in nucleotide metabolism is balance between the amounts of any of these guys. Balance is very important because, as I said, if we get too much of one versus another, if we get too much out of balance, we have mutation. Another thing that's interesting here is that AMP is a feedback inhibitor of this enzyme. And GMP is a feedback inhibitor of this enzyme. Meaning that if we get too much GMP, it's going to shut off its own synthesis. If I get too much AMP, it's going to shut off its own synthesis. So the cell is very careful. I don't want to make too much of this. And yes, I'm going to take energy from the other one so that I have the proper balance of all these guys that are here. Okay? Now, this figure is drawn to show you the many things that can come together and inhibit what is essentially the first enzyme in the pathway. The first enzyme in the pathway. The first enzyme in the pathway, I'm going to give you the name. I'm not even going to hold you responsible for it. Okay? It's called PRPP aminotransferase. All right? Yeah, it's a mouthful of a name. PRPP aminotransferase. Now, I like to describe to students how this enzyme is regulated because it's really kind of cool. And again, it shows us the importance of this balance thing that I'm talking about. All right? PRPP aminotransferase has a regulation that is sort of like feedback inhibition. But it's not exactly like it. Now, what does that mean? Okay? When high levels of AMP or ATP accumulate, the enzyme is partly inhibited. When high levels of GMP or GTP accumulate, the enzyme is partly inhibited. When high levels of AMP, GMP, ATP, GTP accumulate, the enzyme is completely inhibited. So only when we've got a lot of these purine nucleotides is the enzyme completely inhibited. Why does the cell have such an unusual scheme? Well, based on what I've told you, it actually makes very good sense. The good sense that it makes is that this guy, let's imagine I have very little AMP in the cell. Okay? I've got an abundance of GMP, GTP, etc. Right? I have an abundance of these guys on the right. I want to balance things. If I turn the enzyme completely off, I'll never be able to make AMP. So leaving the enzyme on a little bit makes really good sense because the enzyme can start this pathway and get down to here, and what's going to happen when it tries to go over here? It's going to be feedback inhibited. So now this enzyme being slightly active allows it to start building up and building up and building up this until eventually the levels even out. Okay? So it's pretty cool. So we can see with this system I've shown you here that cells have a very cool system for balancing the relative amounts of the adenosine nucleotides versus the guanosine nucleotides. Okay? They have a very good way of balancing those two out. Okay. Now, all this figure that I started to show you before just showed you the individual reactions. We're not worried about the reactions. Okay? There's aspartic acid, for example, coming in. All right. Okay, so the cell has made AMP, the cell has made GMP, and they've got good control of that. Cells also break down the nucleotides. Yes?
So when you say like it's being balanced, it must be like more finely tuned than that, because ATP is used as like sort of a general energy currency in a lot of other reactions.
Okay. So his question is, there must be more to the balance than just equal amounts because ATP is used for a lot of things. I think that's sort of your question, right? Okay. And he's exactly right. There's more ATP in the cell than there is any of the other nucleotides because it's used more for energy purposes. So the balance is relative amounts. Okay? So if ATP isn't at a sufficiently high level, then it's relatively low. So it's not an absolute, okay? Because if it were absolute, if they were all absolutely the same, the cell might be in trouble because it wouldn't have enough energy. Make sense? Yep. But the relative amounts, that relative amount is very, very critical for this balance that we're talking about. Okay, cells do break down nucleotides. You actually heard about this last time, because I talked about the breakdown of purine nucleotides and how it gave rise to uric acid, which gave rise to gout, right? Okay, we can see here purine nucleotides being broken down. There's GMP to guanosine to guanine to xanthine to hypoxanthine, okay, to inosine, adenosine, AMP. Over here we have urea, there's uric acid right there, okay? Xanthine can go to uric acid, and that's where gout comes from. You don't need to worry about this pathway. I'm not going to ask you the pathway, okay? You should certainly know that uric acid comes from the breakdown of purine nucleotides. Right? And when cells have too much nitrogen, they're basically going through this pathway to get down to here so they can start excreting some urea. That you saw from the urea cycle. Okay? Okay. Now, I told you that salvage of nucleotides was important, okay? Because cells don't want to go all the way down here unless they've already got plenty of nucleotides. So if they want to salvage nucleotides, they have some enzymes that allow them to salvage things. So here's a base of adenine that might be floating around a cell as a result of breakdown of some nucleic acid. The cell says, wait, instead of breaking this down, let's use it for something so I can attach it, okay, in this case, to a PRPP, which is basically a ribose, and make AMP very easily. There's a reaction I can do very easily. No, you don't need to know the reaction. A lot of things I'm telling you don't need to know today, okay? Okay? So this is a really good example of a salvage reaction that a cell might use. One reaction, and bang, it's got an adenosine nucleotide. All right? Here's another related salvage reaction. Let's say I have guanine, and I want to salvage it in the same way. Okay? For the moment, ignore the one on top. All right? I have guanine, and I want to salvage it in a similar fashion. Well, there's an enzyme that is an important enzyme. It's called HGPRT. It's got a big mouthful of a name. It's called hypoxanthine guanine phosphoribosyl transferase. Blah. HGPRT. Why do I tell you about this enzyme? This enzyme is very important for salvaging purine nucleotides. And you might think that salvage is something that's a relatively insignificant component of nucleotide metabolism, because, I mean, if cells can make it from scratch, why is salvage of nucleotides critical? Okay. Sorry? It's less energy. Okay. And so you think, well, maybe there's an energy consideration, but it turns out there's some really bizarre things that can happen when cells lack this enzyme. Okay? I'll give you a real good example. All right? This enzyme is deficient in people who have a genetic disease called Lesch-Nyhan syndrome. Leschnyhan. All right? Lesch-Nyhan syndrome is caused by the lack of this enzyme. And when this enzyme is deficient, people who have this syndrome have a bizarre phenotype. Okay? They have severe neurological problems, one of which is they tend to eat their own lips. I'm not making this up. Okay? They will tend to eat their own lips. Right? They have to be physically restrained because they will eventually just chew them all off. Okay? Now, it arises from a deficiency of this enzyme. Kind of odd, right? Very odd phenomenon. So, all enzymes at some level we think are obviously are there for a reason. They're all there as important. So, salvage is an important process. That's a message to take away with this. Okay. Those are purines. Let's think about pyrimidines. Let's go through and talk about every reaction in the pyrimidines. No, let's not talk about every reaction in the pyrimidines. It would be a waste of time, just like the purines were. All right? The purines and pyrimidines do have significantly different pathways, but they both have about 8 to 10 steps that they go through. Okay? We start with very simple things for making pyrimidines, just like we start with very simple things for making purines. All right? Here's some of the simple things. There's bicarbonate, there's glutamine, there's ATP, there's water, and we start putting things together. What comes in? We see aspartic acid coming in like we saw before. Okay? We see hydroxide coming out. We see electrons coming in when we're doing a reduction here. Okay? We're seeing some fairly simple things that are happening in the synthesis of pyrimidine nucleotides. And just like we saw in the purine nucleotides, balance is very, very important. The relative amounts of the individual nucleotides, very, very critical. Now, you've already seen the enzyme that helps in this balance process. Does anybody know what it is? We've talked about it. I'll give you a hint. We talked about it as one of the first enzymes we talked about in the class. What's that? You took your answer back? Is that right? Okay. ATCase. Very good. Aspartate transcarbamylase. Should give you a bunch of extra credit for that. That's good. Okay. ATCase was the enzyme that I talked about very early, and the reason I talked that I said it was important early was because it was an example of an enzyme that exhibited allosteric behavior. It exhibited feedback inhibition. And it also helps to balance the relative amounts of purines versus pyrimidines. We haven't seen that yet. I'm going to tell you how it does it. I'll remind you how it does it because you've already heard it once. Okay? This enzyme is allosterically inhibited by the end product of the pathway. The end product of the pathway is CTP. CTP inhibits this enzyme. Okay? This enzyme is activated, this enzyme is activated by ATP, a purine nucleotide. If cells have more purines than pyrimidines, the enzyme will be activated so that it can start filling up the pyrimidines like it's got the purines. If there's more pyrimidines, relatively speaking, than there are the purines, then CTP is going to win the race and it's going to turn the enzyme off. Okay? So ATCase plays a very important role in balancing the relative amounts of purines versus pyrimidines. And I'll show you another thing that helps to balance the relative amounts of UTP versus CTP. And you're thinking, what about thymine? That comes later. Okay? That comes later. All right. Notice that when we go through the synthesis of the pyrimidine nucleotides, the very first nucleotide we see is UMP. UMP stands for uridine monophosphate. U, of course, is what UMP is, of course, a precursor of UTP, which is used for making RNA. How do we go from UMP to UTP? We put a couple phosphates on it. What kind of enzymes are going to do that? Kinases, right? All right. So kinases put those on. So once we get to UMP, we've got a couple steps, and we're at UTP. And then UTP can be converted into CTP. That's the order in which these processes happen. Okay. There's a kinase. There's a kinase. All right? I'll tell you something very cool. This kinase is a special kinase. Converting UDP into UTP, catalyzed by a special kinase known as NDPK. Again, it has a longer name, nucleoside diphosphokinase. NDPK. Now, the reason it's a special enzyme is for any students that ever study nucleotide metabolism, they love this enzyme. Why? Because NDPK not only works on UDP to UTP, but it works on every diphosphate and converts them into every triphosphate. So if this were a CDP and to CTP, it'd be the same enzyme, NDPK. If this were DADP and we're going to DATP, same enzyme. Okay? So NDPK catalyzes the conversion of every nucleoside diphosphate into every nucleoside triphosphate. No exceptions. Every single one. And you might say, well, where do we get ATP from? Can we make ATP this way? And we can. The enzyme can use all the triphosphates as well. So it could, for example, use GTP to GDP. It's a very flexible enzyme. A lot of energy sources, a lot of substrates that it works on. Very, very interesting enzyme. Okay. Blah, blah. Regulation. Okay. Here is UMP inhibiting an early enzyme. This is carbamyl phosphate synthetase. Actually, is another name for ATCase. It's not shown on here, but CTP is coming back, and it will actually. I'm sorry, I got the wrong one. CTP is coming back and inhibiting aspartate transcribamylase here. This is the thing that makes the precursor necessary for aspartate transcribamylase. Okay? But in any event, this feedback is what's stopping this overall process. The one thing that's not shown on here is that this enzyme that goes from here to here is actually inhibited by CTP also. We won't worry about that. Okay. Oh, just did that. Sorry. Breakdown. All right. Breakdown of the pyrimidine nucleotides also occurs, but it doesn't have any significant health. Remarkably, that's the first time that's happened this term, you know? I applaud you guys. That's good. All right. The breakdown of pyrimidine nucleotides happens also, just like the breakdown of purine nucleotides. But there aren't as many issues or problems associated with breakdown of the pyrimidines as there are of the purines. Perhaps because the breakdown process is actually a bit simpler. I'm not quite sure. All right. Now, the last thing I'm going to tell you about is how do we make the deoxyribonucleotides. Deoxyribonucleotides are made from ribonucleotides. And the starting material for deoxyribonucleotide synthesis are ribonucleoside diphosphates, meaning the starting materials to make the deoxyribonucleotides are CDP, UDP, GDP, and ADP. Okay? As I said, T comes later. We haven't gotten to T yet. All right. The enzyme that catalyzes that, there's one enzyme that catalyzes all those as well. One enzyme. It's called ribonucleotide reductase, which you're welcome to call RNR. It catalyzes the conversion of any of those diphosphates into what become deoxydiphosphates. So, for example, if I start with CDP, I end up with DCDP. What it's doing is it's converting the ribose to a deoxyribose. If I start with GDP, I end up with DGDP. If I start with ADP, I end up with DADP. And if I start with UDP, I end up with DUDP. We haven't gotten to T yet. Okay? Now I'm going to spare you the details on T. T is a little complicated, but I will tell you that T is made from DUDP. There's several steps involved. The result being that only after we've made DUDP do we ever end up making DTDP. Okay? And it's a little complicated. I think it's not necessary for us to go through that. This shows up here a sort of a convoluted pathway by which this all happens. But suffice it to say, what the enzyme is doing is it's converting this guy into this guy. The only difference being right here. The oxygen is being removed, replaced by a hydrogen. Okay? That's all that the enzyme is doing. Now, this enzyme has a regulation that's really complicated. So I'm going to give you the big picture. The big picture is this enzyme balances the relative amounts of all of the DNDPs, which means it balances all of the DNTPs by extension. So all the deoxyribonucleotides are balanced thanks to what ribonucleotide reductase is doing. It's an elaborate scheme. It's a complicated scheme. We don't need to worry about it here. If you're curious, I'd be more than happy to tell you. But it's very cool. So, yeah. So his question is it done by need? And the answer is basically yes, it is. Okay? Too much of one will favor synthesis of others. That's basically what it comes down to. Okay? All right. Now, I would love to dive in and tell you guys all about signaling and all about thymidine nucleotides, but I decided you've had enough this term. Yes. And though I was tempted to, because, I decided maybe I should just really lay it on thick here for your final, I decided not to do that. So I'm not going to go through signaling. You're not going to be responsible for signaling. And I thought we would finish up with some fun, kind of like we've had during the term. Extra. You guys want everything. So the worst I can say is no. The worst I can say is I'll take points away from you. Oh. You thought I couldn't do that. I'm the evil professor. I can do anything, right? So, yeah, no, I'm not going to do that, obviously. Anyway, so I thought we would finish, and I would open this up a little bit. I've got a couple songs I thought I would play. I've got a YouTube and another one that I thought was very relevant for the weather that I would play. And then I thought if you'd like to request a song, I haven't given you the opportunity to do that. I'll pull up my songs and we can decide on ones to sing if you'd like to do that. Would that be fun?
Yeah.
Okay. So if you want to leave, now's the time to leave. We're not going to do anything more that's new that you're responsible for. I'll let everybody shuffle and get away. So I've got a song that is perfect for the weather today, okay? So let me pull that up. Let's see. Source audio. Okay. And let's see. All right. So this one is one I wrote last year when we had this really wet, early summer, and today reminds me a lot of that. You can sing. I won't sing. Birds. Appropriate today, I think. Okay. So, the person who, if you go on my webpage, you'll find that there's a lot of recordings there, and those, of course, aren't me singing them. The person who's responsible for most of the recordings is a former student in my class, and he was a... Hold on. You've heard that one before. Oh, come on. Shut up. Shut up. Where's it at? I can't find it. There we go. Okay, thank you. All right. Anyway, so he was the guy who did a lot of recordings. That wasn't that young man, actually, but somebody else. He was in my class, and he was a former opera singer. And the guy was incredible, and he came back to school to go become a medical doctor. And at the age of 40, it's a true story, he got into OHSU medical school. And he's currently there right now, and he's still recording my songs. Very cool guy. His name is David Simmons. Wonderful guy. All right. So I thought I'd open it up and let you guys, if you'd like to pick out a song or two we could sing, we'll do it. So I'll scroll through them slowly, and you can decide what you'd like. And if it's too hard, I won't sing it, but if it's not too hard, we'll do it. Any thoughts? Should I pick? Should you pick? What's that? My favorite. Oh, boy. Gluconeogenesis is one of my favorites. Okay? I like gluconeogenesis. Okay? And we've done that one. Let's see. What's a favorite that we haven't done? Let's see. Let me think. Oh, well, one we haven't that's very long is one of my favorites, is Central Dogma Zen. And the reason I don't do it is because it is very long. It's to the tune of Those Were the Days, my friend. You guys know the tune? Da 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 da. No, that's Those Were the Days. This was an old song that the Beatles had a woman record back in the late 60s. Once upon a time there was a da 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 dee da dee dee dee. All right. Anyway. It wasn't the Beatles themselves. It was they had set it up for a woman to record. Yeah. All right. How about I tell you what? Okay, a fun one. It's a fairly new one also. Is the vision thing. We haven't talked about vision here, so it may not make a lot of sense, but it's kind of fun to go through. All right. It's to the tune of the Star Spangled Banner. Did you know you can see in the dimmest of lights with your rods and your cones and the retinaldehyde found in rhodopsin? It's got a bond-shaped as cis, but it changes its state when a photon gets it straight. Then the signaling kicks in thanks to a transducin, 'cause its GTP ways turn on diesterase. So gated ion channels stop charges from passing through, such as sodium +1 and calcium +2. Okay. All right. No suggestions? What's that?
Did you write all of those?
Uh-huh. All right, I'll tell you what. I do have one last one that I think is consistent with my anti-smoking campaign that I've been going through this term. It's actually a YouTube video, and it's to the tune of I Left My Heart in San Francisco. And it's called I Lost a Lung. Okay? This is the opera singer.
I lost a love from smoking camels and emphysema. It seems to me you see those nicotines and tars leave alveolar scars. My raspy throat will often show from the smoke. I've no respect for R.J. Reynolds and its corporatocracy. Now when I hear the name R.J. Reynolds, I only think
And that was someone I knew who died of lung cancer. Yeah. So, all right. I think that's all I have, folks. Hi.
I really enjoyed the class.
Oh, good. I enjoyed it. It was a lot of fun. You guys are great.
Too bad he's got it.